I should have known.
No, I don't read anything. I just see the bottom line. Very disturbing.
Oh, that's.
I know.
There's so much homework to do.
Yeah, you just see
I kept doing it in the class, like I'll do it tomorrow, I'll do it tomorrow. Oh, yeah, well, yeah. It's. Yeah. Well, like. How's it going? Are you going to Tony? Oh, it's going okay. Apparently, it's just a cloud breaker recording my phone.
like a different umbrella.
Yeah, I did. It didn't look like it was oh. Sorry.
Yeah, I just gotta like call my ex after like so I could be that so I like find her address. What the heck?
So I get back in the ship.
Did you have to ask her? Her address, phone number, where she was born.
Wait, what? Like, did they specifically ask for like extra?
She's like, she meets like yellow.
Once better. And then it was just like so from my forehead. I saw that I saw that photo. I saw just texted me there, but I just thought it was like a dude or a security or something. I should have gone.
Like that.
All right, let's start. So, last time we were working on the complex power. Let's get started. Okay, so let's start taking attendance. MSU people, just type in the chat MSU so I can take your attendance by the end of the class. And we'll begin a new section now. The assignment related to homework 1 will be posted on Monday. So now you are able to solve at least the sections 2.1, 2.2, 2.3, probably 2.4 also today. And we'll finish the chapter probably sometime next week, and we'll begin with chapter 3. I'm thinking of having midterm 1 by the end of the month of February, but let me check our advance on chapter 3 during next week, and I'll confirm the date. It will be very likely the date posted on the syllabus because I'm quite confident on this rate we'll be able to finish the material even before the midterm. But I'd like to leave some time so that the people could really spend some time on the assignment 2 also. And maybe we could do some solving session for the problems for both homeworks. So let's see what will happen, but I would encourage everyone to get started with homework 1 as soon as Monday, okay? Because typically the homework will be online for a week, and after that it will be locked. So there'll be no late submissions after a week of posting the homework. So now, yeah.
So the homework will be posted on Canvas and due on Canvas?
Yeah, definitely. Yeah, you could upload that there. Because the grader would need to access those files, so it'd be much easier for him to correct through Canvas. As a quick reminder, we were working on the phasors, the instantaneous powers in different loads at single phase level. We've gone through the real powers, reactive one, power factor calculation, power factor correction, and we went over the complex power. So we still have the network equations. Actually, it's the network representation of a circuit in power systems, and we'll get into the three-phase circuits, in particular the balanced ones in different structures, and we'll make some extension for the power calculations in those circuits. So I think we'll have some repeated section here. So instead of doing the calculations on a single phase, the only modification that we'll have here, we'll have 3 phases. So we'll repeat everything just with little modification. Okay? So today we'll be starting with the network equations. I think I've already opened that. Okay, so a quick reminder. Do you remember the KCL and KVL laws? What are they, or what do they mean? Can someone remind us? Yeah, what's that of the loop? The sum? Yeah, okay. What about KCL? Yeah, but it's not within a loop. It's at a node. Yeah, so let's say I have here a voltage source and a number of loads. So for KVL, the sum of those should be equal to 0 over this circuit. So it could be plus, minus, plus, minus, minus, plus, plus, minus. Anyhow, the sum of those voltages have to be 0 within this circuit. So if I apply KVL here, it must be equal to 0. But for the current, we don't consider a loop. We consider a node by itself. A node could be any junction of any type. So the important thing is that the ingoing and outgoing currents, let's say here I have I1, I2, I3, I4. No matter what's their direction, they should add up to 0. So we expect to have some positive or negative currents so that those all add up to zero. They are all positive. They will not be definitely zero. Okay? So this is important here because we make some extension to that. When we are solving those large circuits, actually we are applying those same simple concepts, but on a larger scale. So typically, in the case of steady state in the power system, we will be using all those theorems that you learned in circuit analysis 1 and 2, I think, including the nodal analysis, mesh loop, superposition, source transformation, Thevenin equivalent, or Norton's, because they'll help us understand how the power flow happens. In particular, you'll be solving very small circuits by hand, but we should know how that happens because typically a power system software will be making all the calculations for large-scale circuits, but we need to know how those little things work out. So in case somebody asks us, how would you able to do that thing in the software, we could know how things work out. So let me define here a few things. Typically, I use V for voltage, but in this chapter, for some reason, they used E. E denotes voltage here. So here we see like ES1, ES2, ES3, it represents like the phasor voltage at node 1, node 2, node 3. So I'll try to stick into those names so that you don't have a lot of V's and E's. Typically, E is used when you are doing like EMF calculations for motors or generators for the generated voltage. But I don't know what's the reason here. They are using E, so we'll stick to that. I think there's something good here that they are trying to explain for us the network equations, or in other words, obtaining the Y bus of a circuit through an example. And you'll be solving something similar to that later. So let's begin with this typical circuit. What could we see here? We are seeing a number of nodes, noted 1, 2, and 3. We see a different types of impedances around. I can see some capacitors with negative impedances. I see some inductors with positive impedances, positive J. This is typical. I don't see any resistance, which is fine. And I see some representation of voltages here. So typically, when he's measuring ES1, he's measuring the voltage at this node, from 1 to the ground, okay? This is a typical measurement. I don't know what they do downstairs in the labs, but typically, when you're using a voltmeter, you put the positive at the point that you are willing to measure, and the negative must be going to the ground. So the voltage measurement will be from that node to the ground. You cannot measure really from one node to another. You have to have a ground for measurement, because this is how the voltmeter will see the circuit. So you could put the voltmeter here. I don't know if you can see my pen. No. I cannot show you the pen on the PDF. So let's say we have this section of the circuit. I'm not drawing all that. I don't know what's wrong here. And this is 2, this is 1, and here's the ground. Okay? So if you were in the lab and I asked you to do some measurements, I hope they trained you on that. So you'll get the positive and you put it at this point, let's say. And you put the negative here. So the measurement would be, how much will be the measurement? Yeah, definitely. You are measuring through a wire. The V of the wire is 0. What about the current measurement at that point? At first, the ammeter should be in series. Okay, it's not attached in parallel. It must be like a flowing element here. So the current that we moving from that point would be 0 or more. What do you think? Will be any current moving through or no? Yeah, there must be current actually flowing in the circuit, unless it's open. If it's open from here, there's nothing flowing in the circuit. But the value of this current will be typically equal to the voltage V10 from here to here divided by this. And you should subtract from that E1 divided by this impedance here. Okay? This is something I hope that they taught you, and that here, let's say impedance. This value here. Okay? So this is quite important to know here so that we see how things will work out. The second thing, I don't want to get too deep into electric circuits, but typically when you have some impedance and a voltage source in series, is there any transformation I can make to preserve the current and the voltages for this little circuit? This is R here. What could I do? Is there any transformation I can make to preserve the physical quantities but change the structure of the circuit? Yeah, exactly. So you put here a current source and you put the same R and you try to preserve the polarity. Okay? So those are equivalent to each other. No change. This is typically needed if you're making some circuit reduction. You make a lot of those changes back and forth so that you make the calculations easier on hand. So here they'll be doing the same thing, actually. If we go from this slide or this part of the question to here, they made the same transformation for a reason. Typically, we use V or U equal R, I. But if I want I to be present here, I have to divide V by R. Okay? But I don't like to see this term, 1 over R. This is the resistance. Okay? So 1 over R could be represented in another quantity, which is called the admittance, which is the inverse of this value. And then I'll have another structure. I don't know what to call it, but let's call it Y equal I. Okay? So in this representation, I shifted the equation in terms of voltage to be in terms of current. Okay? So here's the main change that happened on the R quantity. I just inversed that value. And here they made the same thing. So they changed the structure of the circuit and they got the inverse of those values. Okay? Just 1 over all those. So this one was 1 over 10J. It came out to be minus 10J. Okay? And you see the unit S of that admittance. So I think now this is the first step, transformation. I don't typically care about representing those current, okay? And even you don't need to put those voltage sources in the circuit. So typically you'll be just getting some circuit with some impedances and you just have to get the transformation to that. So let me make it easy here. I'll put this like 1J, minus 2J, 2J, 3J, or minus 3, and this is 1J. So the only thing that you need to do, you just get the inverse of those values and you recreate the circuit like that. So you put 1 over 1j s, 1 over 1j s, and you just complete the circuit, okay? There's no need to show me the voltage and current sources transformation. I'm pretty aware that you know that. Then, this is how typically, so as I have said, that we need this form, I equal Y times V, okay? So this is how every circuit has to be transformed and represented for a reason. Because if I want to make any voltage calculations, I would need this structure so that I make any modification on the currents and I will observe the output voltages, how much they would be. Okay? So the only thing that won't be changing is that large Y matrix. This will be the circuit representation. And this will be critically important for power flow analysis. Another extension for this matrix will be, after obtaining the Y matrix, we'll be able to obtain the Z matrix or the Z matrix by inverting again Y, which would give us another new matrix, and that would be used for short circuit analysis or fault analysis, which we'll not cover in this course. It's typically covered in the 5540 course. Okay, the first 2 chapters from that course. I'm pretty aware about them because there'll be a chapter about symmetrical components, and then the other chapter will be fault analysis, which I think those are the most important thing in that course. So for now, and actually they review those in the other course in the first few weeks. So our important thing here to get this matrix in the right way, because after that, any calculation you would make, it could be wrong if all those numbers are wrong. Okay? So I'll show you here how we will be able to get this in the correct way. So some quick observations. Do you see any like salient feature in this matrix? I have a very strong math background, linear algebra, and a very advanced courses in that. But let's talk in a general way. How do you see this matrix? Is it quite special matrix, or is there something like interesting about it? Look into the numbers. At first, it's a square matrix. Okay, so it's n by n. This is a great characteristic of matrices. Otherwise, you'll not be able to invert that matrix or do any other calculation. The other important thing, which would save you a lot of time in the exam, and don't tell me we did not have time, because it's a symmetrical matrix. You really need to remember that. It's a symmetrical matrix, which means it's made up of 2 triangles, repeated ones. So if you calculate half of it, do not repeat the calculations. So you'll obtain Y11, Y22, Y33. Let's say we have 3 nodes, so it will be 3 by 3. Okay? Once you obtain those, you just need to obtain those 3 other values, and the rest, they are just exchanged, okay? They are the same values. Do not repeat those calculations, and things actually get worse if I give you a big circuit, which is 4 by 4 or 5 by 5. Okay? So we'll save almost half of the time by just copying those values. I see too many people, they do all this and they repeat those again during the exam. It's fine in the homework if you do it twice, but in the exam, you'll be really wasting time on something not needed. Actually, a good check. If you get like y12 different than y21, there's something wrong in your calculations. Okay? Those are very important checks for later. So, how we would be able to calculate those values? So, as we have said, we obtained the inverse of each impedance. And now we have two different types of calculations. The what do you call it? Self-admittance. Yeah, it's called self-admittance and the mutual admittances. Okay? They are here. I was just checking their names. So the self-admittance are those diagonal values. Okay? So if we have 3 nodes in the circuit, we'll have 3 self-admittances for each one of them. The mutual are between the nodes, internode. So between 1, 2, 2, 1, 3, 1, 2, 3, things like that. And there's something different in their calculation. For the self-admittances, you have just to sum all the admittances connected to that bus. But for the off-diagonal elements, which includes all those mutual values, they have to be multiplied by -1. If you don't do that, your matrix is wrong, okay? And all the subsequent calculations will be really wrong. Different, much different. So here, I'll do few of those. So let's begin with Y11. So what would be that admittance value? Self-admittance. I need to add up all the connected elements to the node 1, which is 3j minus 10j, which is minus 7j. Okay? Y22 has 1, 2, 3, 4. 4 elements. Okay? So you add them up all. For Y33, it's the same thing. You have like minus 4j plus 1j minus 2j. So let's check those diagonal values here. We see like on this calculation, 3j minus 10j, which is minus 7j. For the other one, it's 3j minus j plus j minus 2j. And for the last one, it's the same thing, minus 4j plus 1j minus 2j. Okay, so we're done with the diagonal elements. So we are left now, at first, this is like a 3 by 3 matrix, as we have said. So we obtained those values. Those are fine. We still need those 3 off diagonal values. So this one would be Y12. Okay? This one would be Y13. And this would be Y23. Okay? Depending on its position in the matrix. So let's look into Y12. It's from here to there. What about now? Good. Okay. Okay. So anyone, what should be the value Y12? Yeah. I don't like to put J at first, so, but it's both are fine. What about Y13? Okay. What's the value of Y13? This is 1. This is 3. No, we cannot do those connections. There's no direct connection between 1 and 3, so the value would be 0. Okay? Do not add up. This is good that you figured this now, because some of us might really just add them up, but there should be a direct connection between the nodes. Okay? What about y23? We have those two connections. So the equivalent circuit of that would be here. And then we got those values. So y13 will be 1. So we got those 3. Immediately, you can just copy and paste those values here. Okay? And we're done, because it's a symmetrical matrix. So the equivalent matrix that I'd like to see is this one. Okay? And from there, we can do whatever calculations that you want. So typically, you'll have in your assignment or your test a similar question, maybe a little more nodes, different structure, but it should be the same concept. So I think I'm done with this little section, and we still have some time to start with the next one.
Back real quick.
Okay.
Why is the 3 negative for
y12? Because it's an off-diagonal element, so you have to multiply by -1. Okay? It's listed here, I think. Yeah, off-diagonal elements, you have to multiply by -1. So here, let's take note of those two things. For diagonal elements, we just add them up, no minus, no negative value. But for off-diagonal element, you have to multiply by -1. Okay? Any other question?
Can you explain what that means?
Yeah. So in a square matrix, this applies only to square matrices, which are n by n type of the structure. So those are called the diagonals. Okay? Those typically we use this diagonal because the both are the same. So those are diagonal elements. Everything else is called off diagonal, which does not lie on the diagonal. So typically in our circuit, we use this as our main diagonal, and we do those off diagonal calculations, and then we copy those values to the other half. Okay, this is only for square matrices, but in real life, you might have a matrix like 2 by 3 or 4 by 3. Nothing applies there. Okay. So now we will extend our work into the balanced three-phase circuits. So here he's making an introduction for three-phase circuits, Y connections, line to neutral voltages, line to line voltages, line currents, delta loads, delta star conversions, and the equivalent line to neutral diagonals. So each of those topics will be covered. So at first, let's do it very easy and simple. Here we are talking about 3 loads instead of 1, and this is typical in power systems because for many reasons, transferring power through 3-phase systems tends to be much more efficient and better for power flow. It would cost us much more if we use single-phase transmission or distribution. So anyhow, since 100 years or even more, they figured out 2 structures, the star and the delta. Okay, this is star, this is delta. There are no other current connections in the power system, and with almost like 90% of the connections are of this type. Okay, very few elements are connected in delta. This is by default. I don't know why, but the majority of devices came out to be utilizing this type of circuit. My inference is that the star connections have some good thing, is that there's a node here which could be grounded. And this is very important because in the case of a fault, there's a pathway for the extra current to flow out of the circuit, okay? But in the delta connections, there's no connection like that, okay? So if something happens here, it'll be flowing all the time within that loop. So there might be much more damage. But for most of those star connections, they are grounded. Mainly if they are large circuits or so, or motors or whatever, they always have grounding. And that thing gets harder with delta connections. So this is actually my own inference why there's much preference for the star loads. So anyhow, let's start with the balanced Y connections. A circuit is called balanced whenever the three loads are equal. Okay, so looking into this structure here, we see a source and a load. One of them is in the star connection, and the other one is a delta. Okay, so I think it looks clearly here who's the star and who's the delta. The source is in a star connection, and here you see the N, the grounding thing, but here it looks like a connection connected to the delta. You see here? It's connected to the terminals of the delta. It's not within the delta. So there'll be quite a difference in calculations between phase and line currents between the two structures. So in this situation, and this is typical in different exams, they'll give you this type of structure, either like star, delta connections, star, star, delta, delta, or delta star, okay? So now we are dealing with this situation. So three loads are balanced. It means those three are equal, okay? Or at the generation side. And typically, also at the load, they are equal, because we see here those ZY, they are equal, okay? So those connections between the small letters and big letters, they are just outer connections at the terminals of both structures for C, A, and B phases. We have three phases, AN, BN, CN. And here we have actually a positive sequence. There are two types of connections or sequences, positive and negative. So the positive is clockwise. The negative is anti-clockwise. So here is a positive connection, which means I have EAN, then EBN, then ECN. For a negative connection, which we'll talk about later, it will be EAN, ECN, and EBN. So we will reverse the B and C junctions, okay? And here we see power flow from small c to big C, because this is the generation, this is the load, and from A to A and from B to B. And we see the back connection, which is IN, from the delta to the star. Why do you think we have that thing there? Why should we have that IN? Can I just remove it? Let's remember the KVL and KCL. I hope someone of you figured out why do we need that connection there. Even there's no impedance or anything, just a wire. MSU people, anyone? Anyone in class figured out why do we need that connection? Yeah. No, it's not about the reference. It's related to those two. Actually, not easier. They make it valid because you have 3 incoming currents from the phases. You see CC, AA, and then BB. So 3 are incoming. There should be something equivalent outgoing at that node. Okay? Otherwise, you just have 3 currents coming in, nothing coming out. Okay? And this applies for KCL. So let's stay with KCL now. But in a good case, how much should be the sum of all those? Yeah. In the normal situation, the sum should be equal to 0. Otherwise, there could be a fault or short circuit happening somewhere. Okay? So this is quite important here to see. Now, we'll start doing the calculations. We said we're doing here a balanced system and positive sequence. So now we will begin with our source side, the generation side. And we have 3 voltages, EAN, EBN, ECN. We said these are voltages. So EAN, is that a phase or a line voltage? From its name. This is a phase thing. Phase voltage. You should be aware of those. Because in the tests, we would just say calculate EAN, ABN, ECN, EAB, EBC, let's say. So you should be aware which one is the phase, which one is the line. EBN would be a line voltage because it's between 2 lines. EBA. So it's a balanced system in positive sequence, same magnitudes for 3 voltages, EAN, EBN, ECN, 10, 10, 10. The only difference is in the magnitude of the angle. And they are, I don't want to say equally distributed, but you have an angle of 0, minus 20, 120, and plus 120. Okay, so those are all 120s. Because everything is balanced, everything is running in order. Okay? For a case of negative sequence, instead of this plus, it will be here. Instead of this minus, it will be a plus. And for ECN, it will be here minus 120. Okay? So if I have EAN and EBN, how could I get EAB? Those should be given. You have to start from somewhere. I will provide them. And then you start doing the other calculations, or at least I should give you EAN alone, and then you'll figure out EBN and ECN, whether they are positive or negative sequence, and then you make all the line voltages calculations. So EAB should be equal to EAN minus EBN. Okay? So you do those calculations. Here he represented those 3 here, okay? In this figure. So EAB is actually equivalent to EAN minus EBN. You just subtract those 2 values and you'll get EAB is equal to radical 3 times 10, 30. What can you observe from this value? In comparison with EAN, which is 10, 0, I think. Which one is bigger? How did you know?
By root 3, where the other one is just 10.
What about the angle?
By 30 degrees.
Yes, so they are not in phase. Okay, there's certain lag. It sounds that AAB is ahead by 30 degrees, and it has a larger value by radical 3. So its value is multiplied by radical 3. This is common. So no matter what are the values of AAN, AAB would equal to EAN multiplied by radical 3 and added to that 30 degrees in a balanced system. Okay? And we do the same calculations for EBC and ECA. You just subtract those if you'd like to try and to see. And this is something interesting here to see that the three of them take that structure. But instead of EAN, we replace that with EBN to get EBC and ECA. I think there's a plot here. Okay, this is very good. So we started with EAN, ECN, EBC. We subtracted each two from themselves, and we got EAB, ECA, and EBC. Those two plots are equivalent, by the way. So the only thing that they did, they just added them all together. What's your observation of those two plots or figures? Is there any observation that confirms that we were saying in the beginning? How can I check if what I'm doing is really right from the laws of physics? Well, according to KVL, the sum of voltages in a loop should be 0. Okay, can we confirm that? Well, I'll just do one of them. EAB. So those are vectors, EBC and ECA. So I'll take one of them and add up the rest. So I took EAB, and then I attached to that EBC, and then I attached to that ECA. Okay, so they closed in the loop actually. So this is good because typically those will come in with magnitudes and angles. So if I ask you to draw them, and they don't necessarily start in a nice way. So here we started with 10, 0. I might give you 20 minus 40 for EAN and calculate the rest. So all your angles will be really mix of minus 40 plus 140. But everything, if I ask you to draw them, they should be looking like that. So they might shift in this way, okay, because of those angles. But they should add up all. In case you make those plots and EAB was like that, and EBC was like that, and ECA was like that, this is not good, okay? They do not add up. So, as we have said, the voltages in certain loops should add up to 0, so they should close in the circuit if we made all the proper calculations. Line currents. This is now easy for the star, because typically, if you have those three here, if you have those three phases, and we said how do we make those voltage measurements, I got a voltmeter here and I measured on this phase. So getting the phase currents is easy. I just divide this voltage, which I measured, EAN, by ZY. This is Y here, ZY. So I just divide by that. And the same applies to IB and IC. Okay? So you are measuring those currents along of each of those lines in this circuit. Here he gave us an example because we already have EAN, EBN, ECN. Remember, here we are using the phase voltages. Do not put line voltages. I know too many people will get lost in those in the homeworks, and in the exam. Just focus on what you see on the figure, okay? So make sure here to put the right values, and you'll make those calculations, and they seem actually to be balanced also. Since we have balanced voltages, balanced loads, we'll obtain quite balanced currents, but with different angles. Okay? So if we add up all those obtained values for the currents, they came out to be mysteriously zero. Okay? This is an important check, which means they add up all together to zero. So they confirmed with the KCL law. If this is 1 or 2 or 3, it's fine in a fault case, but not here. And here he made the same thing for the currents. So those obtained values here, he traced them. But we could see like 5 minus 30. So let's say this is our axis here. This is the angle minus 30. So this is IA. And this is minus 30. And its magnitude is 5. I know everyone is good here in math and he can draw them easily. And then this is 5 minus, or let's take this easy one, 590. So this is here. And it's 90 degrees. So I go up like 90. So I get to here. This is 5. Okay. This is IC. And then I put IB, which is 5 minus 150. So it's 5, but the angle is minus 150. This one here is minus 150. Okay. So I got back to IB to 0. Okay. So we made that triangle very easily. This is the same thing. Okay. Let me check the attendance. Dominique. Okay. Yeah. Let's see. Justin. Nikki. Yeah, jumps. Okay. I'm just getting to know the people now. Theodore. Ethan. And Parker. Okay. So we're good to go now. So we'll have a homework posted on Monday and we'll continue those sections.
Yeah, actually, Greg. Got in a little late.
Yeah, you can add up.
Yeah. I'm gonna be 90%.
He's starting out.
Okay. Do you want to shoot? I'm probably gonna go back to Kansas City.
Is this any of your guys like sweater?
No, it's not. Oh, yeah. Thank you. Good stuff today.
Good stuff? Are you understanding?
Yeah.
Good. Good, very good.
Me looking at this though, it makes me think that I probably should read a little bit ahead because you kind of jump right into it, which is nice.
Okay.
Yeah.
I don't know how fast I am now.
Yeah.
But
No, I think it's good.
It's
I think,
good?
I think
It's a
your
good
pace is
pace?
good. Yeah,
Okay,
yeah.
okay.
I think it is good.
yeah, because I was worried about that thing,
Yeah.
but I still have a lot of content I should cover in this class.
Yeah.
So
Yeah.
I hope people, the rest of the class, will be following up. But and I'm concerned. They sent me 5 emails so far, even before the beginning of the semester. They asking me to determine the midterm dates, and I'm not ready to determine
Yeah.
even before the beginning of the class. But and here I always get people getting sick today. But actually, this is a good favor from me to take
Yeah.
attendance.
Yeah.
Because I got situations last semester where people were graduating and they failed the class. So I could not decide if I should push them up or down.
Based on attendance.
So now
Okay.
I'll not take anyone to jail if he's not coming to class. but
Yeah.
in case I get into those problems
Yes.
again,
You have.
or there
that,
are some
yeah.
people like they need few grades to get into A or B or C. So this should show me some commitment, okay?
Yeah. Yeah.
But if someone does not show up,
Yeah.
I cannot really feel at that moment. So
Yeah. That's fair.
okay, very good.
All right.
How was your Minso grade?
My what now?
Minso.
Means so?
Yeah.
Oh, I got an A. Yeah.
Yeah, definitely.
Dr. Choi. Yeah. He's a very easy grader. I would say.
I know. Actually, I saw his.
Did you hear of anybody who failed the class from the?
I hear everyone got an A. Actually,
Okay.
not the. And I checked his reviews. He
Yeah.
got like 35 who are like you see the rating from 1 to 5.
Yeah.
All 5. The same gang which put all the same homework.
Yeah.
Yeah, he has some good ratings. Actually, I was willing to do something like him, like a quizzes,
Yeah.
take attendance, but I
Yeah.
thought this is not really working
Yeah.
based on his class. So
Yeah. Like the daily quizzes where you take a picture of it and then upload and whatever.
yeah, I don't need to correct those or look into them. So
I'll see you on class on Monday.
yeah, see you.
Yeah, I'm going to Branson this weekend. So,
Oh,
you know where Branson is, right?
yeah, I know.
Yeah. My family are there, so haven't visited them in a while.
Your family.
Not my immediate family. My great uncle, and my great aunt.
Okay, have fun.
Yeah.
I think there's some good things to do there.
Yeah.
Interesting. Okay.
All right. Maybe take
See
care.
you.
Yeah. See you.